Hello everybody, I'm Hongzhu, a professor of computer science at the Oxford Brookes University, United Kingdom. It is my pleasure to present my work on continuous debugging of microservices. It is co-authored with my colleagues Dr. Ian Bailey and Dr. Hongbo Wang. I will present the motivation of our research, introduce the notion of continuous debugging, and propose a debugging facility that supports continuous debugging. I will outline the implementation of the debugging facility as it is implemented in an integrated DevOps environment, as well as a scriptable command. I will then report the evaluation of the feasibility of the debugging facility on its overhead and performance as it is now implemented. I will conclude the presentation with a discussion of related work and future work. Our research is concerned with cloud-native applications. Such applications are required to achieve high availability, high reliability, and high efficiency in the use of computing resources. They are subject to continuous evolution too. The current best practice in the industry is to use microservices as the software architecture, use container technology as the runtime platform, and the use of DevOps as a development and operation methodology. Such applications are still very difficult and very complex to develop and operate. The difficulty in the development are caused by the complexity of these distributed systems and the intensive concurrency in the operation of the system. The operation difficulty comes from the heterogeneous nature of the cluster and the platform, the uneven workload on the nodes of the cluster, and failures happens frequently, but the causes of the failures are complicated and difficult to diagnose. One of the most notable difficulties in the development and operation of cloud-native applications is debugging. However, debugging is totally missing from the toolbox of microservice developers, as Levin pointed out. To address these difficulties, here we propose the notion of continuous debugging to complement with continuous testing, integration, deployment, and delivery. It shares a common notion of this continuity with other existing techniques by requiring debugging to be performed without any delay as soon as a failure occurred, and also requires debugging to be performed non-blocking to other DevOps activities. To support such a continuous debugging, we require a debugging facility to have the following features. The first is the debugging should be performed remotely. It enables the debuggers working on a workstation to debug agents running on other machines in the cloud. It also requires debugging to be performed online in the sense that an instance of a microservice can enter and exit debugging mode while it is running. It also requires debugging to be performed on multiple instances of different microservices at the same time. Moreover, it requires the debugging of instances of microservices without interfering other microservices, even they are running on the same machine. Finally, It requires debugging to be non-intrusive in the sense of not to change the code of the microservices, especially without any instrumentation code on the microservices. Obviously, existing debugging facilities do not meet these requirements. Therefore, here we propose a new debugging facility which purposely designed to support the continuous debugging. The debugging facility consists of 3 sets of functionalities. The first is trace recording. A trace is a sequence of instructions or statements that an agent executed in a particular period of time during debugging. The operations for trace recording consists of start and stop traces, where start trace is start recording the execution trace of selected agents and save them to files where the agents are executing. Stop trace is simply stop the recording. Because these trace files are saved on the machine where the agents are executing, therefore we need a third operation, which is to get trace from those remote machines to the debugger's workstation. This is an example of the trace. It shows the agent information, where it is executing, which service it belongs to, and the time it started to trace. It consists of a sequence of instructions executed with the time step and also the source code line where the instructions are generated. The second set of functions of the debugging facility is to take state snapshots. The state of an agent at a particular time moment includes the values of the program counter, variables, and the stacks, and the messages in the queue. The operations are: first, get state is to send the values of PC, variable, and the stack to the debugger workstation. Second, get messages is to send the list of messages in the queue to the debugger workstation. In addition to these 2 operations, we have also introduced the notion of checkpoints. A checkpoint is a location in the program. When the execution hits the checkpoint, in the mood of taking checkpoints, it will save the state to a local file. So the operations are add or clear checkpoints and to start checking or stop checking. Once the state have been saved to a local file, you can use the operation get checkpoints to send the saved state into the debugger workstation. This is an example of get state operation. It shows the information of the agent being debugged, the location of the agent, the service, and the instructions when the state snapshot is made. It contains a list of variables with their names, their data type, and their values. In this particular example, the stack is empty. This shows an example of get messages operation. Again, it has the background information of the agent, the service, and the instruction when the state snapshot is take place. It shows 2 messages in the message queue for where the message comes from, what is the message content, and so on. This is an example of checkpointing. It contains 2 records of state snapshot in this checkpoint process. The first one shows the time, variable values, and stack contents in the stack, as well as 1 message in the message queue. The second record shows a similar information, but the message queue is empty. And in this example, we can see the message is processed during 2 times when the checkpoint is reached in the execution of the program. The third function of our debugging facility is execution control. It enables the debugger to pause, step forward, and resume the execution of the agent on the debug. It enables the observation of the program state and the behavior to be performed. We also have the operation to add and clear breakpoints, which are locations in program code. When the program hits the breakpoint, it will pause the execution. The operation run to next breakpoint enables the programs to execute until it hits another breakpoint. The proposed debugging facility has been implemented to debug CAOPLE programs, which is a novel programming language specially designed for developing microservices. It is supported by an integrated DevOps environment, which integrates a traditional IDE with operational facilities. In this environment, we can write the program code, perform project management, configuration management, and compilation of the program into deployable code. The environment also contains the cluster management tool, which enables the developers to manage the virtual machines, monitor the operation, the performance of the virtual machine. The deployment management tool enables code to be deployed to the cluster. The environment also contains a runtime management tool for the operations on agents, which include the creation and termination of agents on the cluster. It is also the environment our debugging facility is integrated into. Here you can see a set of debugging buttons which enable the software engineer to conduct debugging operations on agents. The debugging facility can also be invoked through scriptable command. Here is the general format of the command and their parameters in the table. The debugging facility is implemented by modification of the virtual machine which implements the CAOPLE programming language. In particular, we have modified the management engine to enable the debugging operation instructions being sent and the result received from remote machines. The logic execution engine is also modified to perform the debugging operations. We have conducted an experiment to evaluate the debugging facility for its feasibility in practical use. The first experiment is about the overhead of the debugging facility to compare with the system without debugging facility. We have designed a benchmark of 6 programs to cover various types of applications and execute the program on the system with and without a debugging facility repeatedly for 100 times each. The average execution times of the benchmark programs are compared. This table shows the benchmark programs and their key features. The experiment has been conducted on 2 different platforms. One is a desktop computer, one is a server. The result of the first experiment shows that the overhead of the debugging facility is less than 3% on average. To evaluate the performance of the debugging operations, we conducted 3 experiments to answer 3 different research questions respectively. The first is the performance of the tracing. The second is the performance of state snapshot. And the third is on the performance of a message snapshot. To evaluate the performance of tracing, we execute the same benchmark, but this time with the tracing facility on and off. The experiment data shows that the trace will only increase the time for execute a program when tracing is on by less than 5%. To evaluate the performance of state snapshots, we designed another benchmark with programs that have 2 parameters. One is the number of variables, which ranges from 1 to 50, and the size of the data held by each variable, which ranges from 4 to 20 kilobytes. For each sample program, we executed 10 times to take snapshot and then calculate the average execution time. The experiment data shows that the time needed to take a state snapshot is linear in the number of variables and also in the size of the data to be state snapshot. The time required to take a state snapshot is negligible. For example, for 50 variables and each holding 1,000 integers, a total of 200k bytes, the time is only 6 milliseconds. To evaluate the performance of a snapshot of message queues, we designed the third benchmark with programs that has different lengths of message queues. It ranges from 1 to 8,000 messages. For each sample, we run the program 10 times and operate the get message operation into different scenarios. One is in the ideal scenario with no other agents running on the machine, and the other is when the workload is high. In the sense, there are other agents running on the same machine at a nearly saturated workload. The result of the experiment shows that the time required to take a snapshot of the message queue is linear in the number of messages in both the ideal scenario and the workload scenario. The time needed to take a snapshot is negligible, where for 8,000 messages it takes less than 120 milliseconds. To conclude, in this paper we propose the notion of continuous debugging and proposed the new type of debugging facility for the continuous debugging. There are some debugger facilities for distributed and parallel computing, but not as strong as the debugging facility we have. Some of them are special for different purposes, such as for supercomputers and for MapReduce applications. Google Cloud Debugger has similar functions, but it has a much higher overhead. And also, Squash is claimed to be a debugging facility for microservices. However, a careful analysis of this functionality, it is far away from the requirements of continuous debugging. For future work, we are interested in empirical studies with professional software developers to use our debugging facility to debug microservices. We're also interested in use our debugging facility to implement automated debugging, especially using the traces. We're also interested in transport the technique to implement debugging facilities for other languages like Java, Python, and Search. Thank you.